Levodopa. If you rearrange the letters, it says Levodope. Get it? Dope as in weed. Levodopa is a drug used to treat Parkinson's disease and its motor symptoms. It came from the herb that is known as Mucuna pruriens and is found in the tropics and is well known for producing itch. This herb has many different species that are found mostly in the tropical regions, predominantly in India and Africa. In ancient times, the seeds of M. pruriens were used in a variety of interesting remedies, especially in the traditional Indian medicine practice called Ayurveda in the Vedic times. Back then, the seed was notably used for its anti-venom and anti-inflammatory properties. As an anti-venom, it has been claimed that if the seeds were swallowed intact, the individual will be protected for a full year against effects of any snake bites. In India, the seeds have traditionally been used as a nerve tonic and as an aphrodisiac for male virility. In case you don't know or forgot what Parkinson's disease is, it is a neurodegenerative disorder characterized by a loss of dopaminergic neurons, which lowers the level of dopamine in the substantia nigra of the brain, leading to Parkinson's patients experiencing symptoms such as resting tremors, bradykinesia, postural instability, and muscle rigidity. And this is where levodopa comes into the rescue. Levodopa is a precursor of dopamine, which is used to make up for insufficient dopamine in Parkinson's patient. Examples of commercially available products include Kinzin as tablets and Duodopa as an intestinal gel. For almost 50 years, administration of levodopa to patients with Parkinson's has helped to significantly improve their smooth motor movement, and lowering blood pressure and increase the production and regulation of human growth hormone, which benefits both men and women. It is the most potent hormone in the human body and it controls the aging process. Let's take a look at the structure of levodopa. It is a naturally occurring amino acid. As you can see from the name, it is an acidic compound. From the structure, we can see a primary arene sitting right next to the carboxylic acid, giving levodopa a little bit of basic property. Two phenyl groups on the left are weak acidic groups that make the molecule more polar and involves in hydrogen bonding. Carboxylic acid, as you might guess, is yet another acidic functional group that can act as a hydrogen bond donor and acceptor. It is also the key functional group that differentiates levodopa from dopamine. Despite levodopa being a polar acidic compound, it is mostly absorbed in the small intestine via large neutral amino acid transport machinery. This is why a high-protein diet with levodopa should be avoided, as it will increase the competition for the amino acid transporter in the small intestine as well as the blood-brain barrier. Levodopa, again the precursor amino acid of dopamine, believe it or not, is already in our body naturally and are exactly the same as the levodopa that we administer. It originates from L-tyrosine through conversion by tyrosine hydrolase to become levodopa. It is then decarboxylated to form dopamine. Now, levodopa by itself doesn't do anything at all. It is only useful once it is converted to dopamine that interacts with dopamine receptors for local synaptic neurotransmission. There are a lot of pathways in the brain associated with dopamine neurotransmission. These are called dopaminergic pathways, most notably the mesolimbic pathway for reward system or positive reinforcement, and nigrostriatal pathway for motor control and associative learning. In general, the therapeutic target for levodopa would be to successfully cross the blood-brain barrier and meet dopa decarboxylase in dopaminergic pathway, to be converted to dopamine for synaptic neurotransmission. Moving on to the extraction of levodopa, the extraction from M. pruriens nowadays is not widely used as a source for levodopa because it is less efficient than synthesis. Regardless, here's how it works. The most efficient way to extract levodopa from M. pruriens is through a process called MWEL 1299. Assuming 100 grams of dried mil seeds are put into the process, it will be defatted with acetone by shaking for 48 hours at room temperature. The defatted material are extracted with water and ethanol in a 1:1 ratio, then add ascorbic acid and shake overnight. The residue are then removed by filtration, then pulled and concentrated. It is then crystallized and recrystallized in hot water to give pure crystals of levodopa of 1.78 grams, which is 1.78% of yield after 4 days of processing. And from that, we can see why the production of levodopa is mainly from chemical synthesis. The most efficient chemical synthesis is called the Ajinomoto process, commercialized and used by the Japanese, that can have a yield of 80% levodopa in just 12 hours of process. And the scale of the production was reported to be 110 tons per year of levodopa.
Now all this sounds very intricate, but how in the world did we figure out L-dopa was appropriate for Parkinson's disease? Back in the mid-20th century, there was no high-throughput screening or any electronic library of molecules to test ligand receptor activities. It was merely an educated guess by a Swedish pharmacologist by the name of Arvid Carlsson in mid-1950s, throughout his research for reserpine, a drug for schizophrenia, he found that levodopa was able to remove the Parkinsonian side effect induced by reserpine. It was later confirmed by the Austrian scientist Ole Hornigwitsch that the postmortem brains of Parkinsonian patients had depleted dopamine levels in the striatum of the brain. In 1961, along with neurologist Walter Birkmayer, they injected levodopa into 20 severely Parkinsonian patients and achieved a temporary miracle, witnessing the transition of rigid limbs to controlled movements for a few hours, which was never achieved before. By 1967, an oral dose of levodopa was developed by Cordiaz, and the large dose was administered to patients with severe PD, and it proved to significantly reduce Parkinsonian symptoms. However, due to the high dose given, the patients experienced side effects that included nausea and vomiting. So how do we make it better? Now, the side effects experienced were due to levodopa being converted to dopamine in the periphery. This meant that very little levodopa crossed the blood-brain barrier, thus limiting its therapeutic effect. And this is where carbidopa comes in. Carbidopa is a dopa decarboxylase inhibitor, which is used in combination with levodopa to prevent the conversion of levodopa to dopamine in the periphery. Ultimately, this allows more levodopa to cross the blood-brain barrier, to produce dopamine in the brain. Now, this allowed to reduce the dosage administered and minimize the side effects experienced, thus alleviating the associated clinical symptoms of Parkinson's disease. With the knowledge of optimizing a compound's pharmacokinetics and pharmacodynamics, scientists were able to create levodopa's little brother, with very similar structures, through chemical synthesis. The compound is called melevodopa. Melevodopa is pretty much levodopa, but with a methyl ester. The esterification of the carboxylic group increases the solubility by approximately 250 times. It's made as an effervescent tablet, and at physiological pH, melevodopa exists in unionized form, whereas levodopa exists in ionized form, thus increasing its lipophilicity to enhance its absorption across intestinal walls with a more rapid onset of action with a longer half-life. Compared to the combinational therapy of levodopa and carbidopa, it is shown to have a shorter Tmax and Cmax, which is an overall improvement. It is currently undergoing FDA approval in the USA. If you don't believe what I'm saying so far, here's some proof. Back in 1969, a major study was completed to measure the effects of oral levodopa in AT patients with Parkinson's disease. 71 of these patients were seen to have an improvement of more than 50% in their general performance, while 90% of patients had a partial improvement of all Parkinsonian symptoms. However, a number of side effects were observed, which include hypotension, nausea, confusion delusions, and involuntary movements. As good as levodopa sounds, there are some negatives. Now, almost 50 years since levodopa was first used, the side effects caused by it are still proving to be an issue. Scientists nowadays are working to counteract these adverse effects by targeting pathways that cause dyskinesia and impaired voluntary movements associated with the chronic use of levodopa in PD patients. A study in 2016 by Miguels involves using Parkinson's disease-induced mice. The effects of combination therapy using levodopa and a modified herbal remedy, KD5040, were measured using a number of behavioral tests. The results indicated that the herb lowered the effective dose of levodopa and alleviated levodopa-induced dyskinesia. These findings suggest that the herb may be used as a complementary therapy to enhance the efficacy of levodopa and alleviate its adverse effects in patients with Parkinson's disease. However, this was only tested in this particular mouse model, and therefore further studies need to be done. Apart from that, different dosage forms are also being developed for more convenient application or administration, preferably a once-a-daily regimen. Researchers have attempted to formulate levodopa into a transdermal patch. However, it failed to reach the therapeutic efficacy of oral levodopa. Currently, researchers are attempting to make an extended-release prodrug out of levodopa and are optimizing an intraintestinal gel application for continuous infusion of levodopa. These two methods will hopefully improve the half-life of the drug. And there you have it, folks. Levodopa, the gold standard treatment for Parkinson's disease since 1970. Although it's somewhat flawed, improvements are surely on their way.